Okay, so thank you to everybody to join this webinar about how to ensure electric drive efficiency and cooling performance while maintaining NVH target. So the agenda of this webinar is below. So I have divided into 4 parts. The first part will be the overview of JMAG for electrical motor design, where we will see how we can use the magnetic module in order to check some check some behavior of the motors. So this part will be done by myself. So I am Zefak. So I am a JMAG multiphysics and super engineer, and I work from Powersis. The second part will consult the thermal aspect. So this part we will done by Mr. Maxime Beaumet. So he will show you how why Cadel scFLOW it is a best tool for to check to simulate the cooling performance of the motors. And the third part will be presented by two experts. So it's about the NVH analysis using Romax Spectrum and Actran. So this part will be shown first by Sami Buskru, so which is a technical account manager from Romax Technology. So Romax Technology is a part of Hexagon, so also Cradle for thermal simulation, and then the second presentation on the NVH simulation will be done by Mr. Roman Botson, which is a product marketing manager at Freefield Technology, which is also a part of Hexagon. And then we will finish by the question and answer. So feel free if you have any question. So feel free to type all your question into our chat box that you will have on your screen. Yeah. Okay. So regarding my part, at the left you can see the process that we want to show you during this webinar. So we will use several tools, so 4 tools, and we will show you how we can make the multiphysics coupling between these tools. So at the beginning, I will show you how to use the magnetic solver in order to, for example, calculate the joule losses and the electromagnetic forces for thermal and mechanical simulation. So for the first part, which about JMAG tool. So not that JMAG it is a finite element software dedicated to any type of electromechanical system. So this tool was created since '83 by Jushu Corporation. So it is a Japan company, and JMAG it is a good tool. It is a standard tool to design any type of electric and transformer. Yeah. So regarding the magnetic module of JMAG, yes, so we know all the standard process of the finite element modeling. So into JMAG, you will be able to run a 2D or 3D magnetic field and analysis, and you have different type of magnetic field calculation. You know, regarding the different application, so we have a lot of application that we can model with JMAG, starting from motor to transformer, also actuator, and so on. So JMAG can be used on several markets, so from automotive to aerospace, also from for academic field. So we can also use JMAG. So if we look the toolchain to design any type of electromechanical machine, So generally, we start from a basic design to the validation of testing. So at each level of the design, JMAG provide you a specific tool to achieve this step. So for example, for a basic design, you can use JMAG Express, which is the which, who is it, it is 2D 2D tool that allow you to create your motor geometry and to get in 1 second all the first basic characteristics of your motor. You can also have you also have another tool for transformer. Then you can switch to a JMAG designer for detailed calculation where you will be able to add some specific condition, make some fine mesh, create some custom coil winding to get the result with more precision. Then after getting a good result, you can then switch to the testing and validation by using JMAG LT in order to convert the 2D or 3D finite element into a single component that you can import into your software, into your circuit simulation software. And you can also use another CAA tool for multiphysics calculation, such as Cadel Spectrum, which is the tool that we will focus during this webinar. Okay, first is regarding the loss calculation. So it is very important to understand how the temperature is generated inside the motor. So for that, we need to analyze the heat loss distribution inside the motor. So for that, to JMAG, you can calculate several types of losses. You can calculate the iron losses, copper losses, steel losses, and also all the iron loss component. For the iron loss analysis, so JMAG will do that into a post processing calculation. So here you can see the process. So JMAG will start by by a magnetic field calculation in order to get one periodic curve of the magnetic field. Then it will apply the FFC to get the different harmonic of the field. Then based on that, it will calculate the total losses by using the material property that you define into the material. So regarding the material property, so you have different type of iron loss property that you can define in order to get the losses with high precision. You have the iron loss density this distribution here, and you also have the hysteresis loop property that you can define in order to get with higher accuracy the iron loss of the magnetic core. So for the electromagnetic calculation, yeah, so it is also important to understand how the noise or the vibration is produced inside the electric motor. And for that, JMAG will use, for example, the magnetic module in order to calculate all the distribution of the forces. So today, we will not show you all the source that produce the noise. So we will only focus on the electromagnetic force. So the force produced by the variation of the magnetic field inside the motors. And this force is this distribution of the magnetic field, yes, is can be created by the input current. So this input current can be a sinusoidal current or a current with different harmonic. Yeah. So into JMAG, you have different calculation method for the forces, and the force that I want to focus today is the nodal force calculation method. so which is based on the Maxwell tensor. So this force is the force which act on each node of the magnetic core, like rotor or stator core. So here you will see that the forces, the automatic force, is the summation of all the nodal forces, which depend on the Maxwell tensor and also the shape function. So the shape function is relative to the mesh form of the structure. Then here you can see the Maxwell tensor that JMAG will use to calculate this nodal force. And you also have the surface force, which is the integration of the pressure. So the Maxwell tensor along the normal of the surface where the force is acting. Yeah. Okay. So let's switch on the demonstration. Yeah. So here you can see the JMAG. This is the JMAG interface. Here you have the project manager where you will have all the model, so 3D, 2D model, and also all the study that you can create to analyze this kind of 3D model. Into your right, you have the toolbox. So the toolbox contain all the material database, all the condition depending on the study that you will create here. You also have some script, and you have a lot of feature that you can use to create your finite element model. Okay, so here this is the model that we will use to make to show you um, the different coupling between JMAG, Cradle, and Romax Actran. So I received this model here. So the first thing I try to create, yes, uh, the coil where I will power the motors. So here uh, I the coil. So maybe at the end I will show you, if I have time, I will show you how to create this coil. Then here I have extract the electric motor, so the partial model. So so into JMAG, you can also use the partial model in order to reduce the size of the model, and also to speed up the calculation. So here you can see that I have made several analyses. So I can show you one analysis that I have run, this one, and here I can show you the result. First, I will show you the multi-field, this distribution here that I got. And also I can show you the joule losses into the winding. Maybe I can play a little bit. Here you can see the distribution of the joule losses inside the winding. So maybe I can add something just to show you the winding. So this is the winding here. I can also show you the current density inside the winding here. Okay. So, I can show you the iron loss into the rotor and stator part. Yeah. Yeah. What one good thing is that into JMA you can also plot the flux line. Okay, here you can see some flux line, yeah, some leakage flux. So yeah, so this leakage flux is the flux which cause the its losses. So its losses into the end winding of your motors. Yeah. Okay, maybe I can also show you maybe the forces. Okay, let me remove the magnet. So here you can see the distribution of the nodal forces into the T of the stator here. So when you are running this kind of calculation inside JMAG, so now you can use the multi-purpose file export tool in order to export some result file for post-processing into an external computation software. So for that, here, so this is the tool to export JMAG result. Here you can select all the output format that you want to export. So for example, for the thermal coupling using Cradle software, so you can use MSA fix MSA Nastan fix file here. Then here, this is the JMAG result. So the input result file is the JMAG result that we have run here. So inside JMAG result, you need to select here. So you need to select the path where you want to export the physical quantity. So for example, here I want to export the joule losses. So I want to export, for example, the joule losses from the winding. So here I will select all the winding part. So here I need to select all the winding. Yeah. Okay, then here I will select the joule loss. This one. Then here I can, because here I have run the simulation using the partial model, so I can also I can convert to the full model using this option. So here I can select extend to the full model. Here I can link. I can say that I want to use the boundary condition that I define inside the study here. So I will see that I will do manually the conversion. I will use the periodic boundary condition that I define into the study. I will also make the mirror along some plane. So for example, I will select this plane here, and here you can select the mapping method here. So you have the direct mapping, and here you have the force density mapping. So the force density mapping, so it will map the joule loss density on each element of the structure. Then here I will click on OK. So here I have you have the simulation step. So from the step 1 to the end step of the simulation. Here you can set the output unit that you want to export with the format. Here I will select the original card. So I will say that here the all the winding, all the winding shape where JMAG will map, will extract the joule loss will be will coming from from the model that I create here. Yeah, so here I will set where I want to save my output file, so I can define the name joule loss. Then I can save. When you finish this, then now you can select export. Then it will export all the CSV, all the format, all the file that you specify here. So maybe I can show you one example of file. So it will open. So here you can see this is, for example, if you select here, if you select, for example, save the file, this is an example of output file that you will get. So here you will get all the mesh element ID, and you will get the position of each element, and here you will get the joule loss density. Yeah. So it is the same. It is the same process when you want to extract the forces. So here you just select the forces and select the part where you want to export the forces, and then here you can specify the where you want to save it, and then export. It will export the forces. But for Romax, we also have we have also created some script which allow you to extract the forces at each two of the stator. So for example, here I can show you what kind of of forces should be export. Here I will select, for example, this face, select the forces, cylindrical coordinate, the radial forces. I will make the summation. So here I will select all the two. So here I have 12 slot. Take some time. So with this option, it will select all automatically all the T of the stator. Sorry. So we're still making some calculation. Okay, then here, okay. Okay, then here I can display, for example, the radial forces. So here you can check the radial forces of each if each two of the stator. Yeah. Okay, so let me go back to my presentation. Sorry. Yeah. Okay, I have finished with the demonstration. Okay, so now this is the general process to export the JMAG result the JMAG result for external post-processing that I show you. So here I also show you the solution that I done with JMAG in order to calculate the Joule losses and the electromagnetic forces for external multiphasic coupling. So I also show you this tool to export different format, different to export the JMAG result into different five format. And to summarize, before making the multiphasic coupling, note that JMAG can allow you to check with high precision all the characteristics of your motor, of the electric motor. So starting from the analytical solution, the analytical design to the system design. So for example, into the analytical design, you can use JMAG Express to to start by create the geometry of your motors. Then you can make a finite, you can switch on finite element calculation in order to check all the behavior, so the magnetic behavior, the force distribution, and also the losses inside your motors. You can also make the optimization, so you can make a classical optimization or topology optimization in order to find some new topology of the rotor or stator, and also check all the possible solution that you can have. So JMAG can do that. You can also check the classic map of your electrical motor. So JMAG are able to create, for example, the efficiency map to plot some copper loss. So the loss this distribution are also the magnetic field or the LQ map. So JMAG can provide you this, and also with the magnetic module of JMAG, you can also make some internal control. Yeah, and you can also create some use JMAG RT to create the 1D component that you can use to make a simulation using a power circuit software. Then you can now switch on multiphasic by extracting some result that you can export that you can export for thermal and mechanical. Maybe I can show you a little bit some characteristic quickly, some characteristic that I have made. So here I have also do some 2D analysis here. For example, here I can show you some control that I've made. So I can show the circuit, the control circuit that I create inside JMAG. Yeah. Here you can see the forces, yeah, and also the current. So you can see the current with harmonic, yeah, harmonic, and also the torque. And here you can see that the torque is converted to the steady state, yeah, with several harmonic. And one thing that you can also do in JMAG is to generate the efficiency map. So here I can show you the efficiency map that I create. And from this kind of efficiency map analysis, you can also plot several different type of mapping. So for example, you can plot the total losses, You can plot the AC copper losses. You can plot the output power map. Here you have the efficiency. Okay. Okay, I think it's good for me. Then let me go to the next. Okay, so then the next topic will be the thermal analysis. So I finish with the first part. Then now Mr. Bome Maxime will show you how we can use the joule loss calculator from JMAG in order to check the cooling performance of the motors. So now I will make Maxime host. I think now Maxime are able to share his screen with us.
Thank you, Didier. Please just tell me when you can see my screen.
Yes, I can see your screen.
Okay,
yeah.
Thank you.
Thank you. Yeah.
So hello everyone. So Didier, great work on the electromagnetic side. Now we'll focus on the thermal aspect of the problematic. So I'm Maxime Baumet, working as a pre-sales engineer for the Cradle product at MSC for the last 6 years now. So as every pre-sales guy, I'm very lazy. So that's why I always wonder, why would it be worse to do something before actually doing it? So here, before moving to the thermal aspect, I would say, of the problematic, why should we care about the thermal aspect? Actually, there are 2 points. The first one is that if you don't care about the thermal problematics, you will get overheating of your system, and it will create some damages inside of it. And as a consequence, it will reduce the lifetime of your products. So that's the first point. The second point is about the product performances, because if you are too high in temperature inside the e-motor, it won't be able to give its full potential, and the performance that you can reach won't be the optimal one that you could expect from your device. So that's worth to wonder about the thermal aspect of the problematic, because of these 2 points, the lifetime and the performance. I think it's important enough to have a look at this. So if you remember about just the previous slide, so here we have a very nice color plot. This is the goal that we are trying to achieve in terms of CFD calculation. But to reach that beautiful color, beautiful result plots, sometimes it could be a long and painful way to get there, because actually in this application, it's always the same. It's about complexity and the level of detail that we have in the CAD assembly, because you will have small gaps, you will have intersection, you will have a lot of parts, and sometimes it's very hard to handle inside the CFD simulation tool. So for us, the good point is that Cradle have at its disposal several kinds of mesh types. So I can hear you wondering, why should we care? Because okay, you have several a multitude of meshing types that you can handle. That's good for you, but what does it bring to us in terms of user? So actually, it's really simple, because here each mesh type will have its own benefits. In this case, you remember that the main challenges are about CAD complexity regarding the assembly of e-motor. Here, I will make a focus on this specific meshing type, voxel fitting one. In a traditional perspective, this is the basic workflow that we can expect for CFD calculation, as long as you have heat exchange to be taken into account. You will start from a CAD assembly. Then you will spend some time on CAD data cleaning. It means that if you have intersection, gaps, and so on, you will need to remove all of them to get parts perfectly in contact. And as you can see here, it can last several days or hours, depending on the complexity that you are dealing with. Then you get, I would say, a clean assembly. Then you will have to wrap parts. Then you will have to mesh it. And traditionally, if we are looking for an OEM traditional perspective, it can last between 1 to 5 days. So it's not piece of cake here. The point about voxel fitting process is to remove manual and very painful operations. We want to replace this manual operation with automated one. So here the point is to start from the same CAD assembly, so including gaps, intersection, and so on. And then we want the mesher to do the job instead of you. So here the point is to reduce this 1 to 5 days to several hours, and during this period, you will be able to have coffee with your colleagues, maybe also to work on something else. We want you to focus on what really matters. And I guess your value is more about interpretation of the result instead of building the model itself. So that's the point of voxel fitting, starting from a complex CAD to get a mesh at the end, but with the least number of manual operation to do. So that seems to be a beautiful promise here, but how could we do that? If we look here more specifically on e-motor application, this is an example of a CAD that we can deal with. Here, between the rotor and the stator, we have 1 millimeter gap here. The point with voxel fitting mesher is that you will ask for level of detail that you want to be kept after meshing. First configuration here, if we ask for something like 1.5 millimeter level of detail that we want to keep, you can see that this value is above the real CAD gap that we have here. In this case, you just need to specify this level of detail, then you ask for the mesh. This is what you will get. Here, the meshing process will automatically fill the gap between the parts. Here, we didn't have to touch the CAD itself. It's all about meshing. But on the other hand, maybe you want to keep this gap because maybe it can be very important in the heat exchange of your system. The only thing that you have to do here is to reduce the threshold that you gave to the software. Here, if we reduce this value to 0.3 millimeter, now the meshing will give you this. You will get the solid parts mesh, but you will also have cells standing for the air gap between these solid parts. That's the point about voxel fitting mesher, okay? To really focus on what we want to consider in the simulation, but if you don't want to spend too much time on small details and so on, the meshing process will automatically clean it for you, okay? And in this typical application, this gap, it's always a crucial question, I would say, because if you are looking for very detailed and high precision results, you will have to take into account this gap. So that's why you should use something quite refined here locally. But maybe if you just want to get a rough idea about the thermal distribution inside your system, maybe as a first approach, you can just modelize this air gap. And in this case, you can also do it with this, with no air gap meshed, but you will be able to just add a thermal resistance to consider. It's always the same question in CFD simulation, is where you put the trigger between precision and I would say calculation speed. That's it. But you have the choice for that. And it doesn't mean that you have to spend hours and days on CAD preparation. So to get a model ready to run for simulation, we have seen that the path can be sometimes complex, sometimes long, and so on. But the good point is that at the end, you have the choice, your choice. Do you want to look more on complexity, on high level of precision? Do you want maybe to go straight to results, maybe in a quicker duration? That's up to you. But with our tools, you are able to do both of them. So after this beautiful speech, maybe I will show you a little piece of software here. How do we set up a simulation here in our tools? So here I will just start from a blank sheet to show you how we would proceed in setting up the model that Didier already performed on the JMAG perspective. So here We'll start with the import of the geometry itself. So here, in terms of import, we can use neutral files such as parasolid or step files, but we can also use native files. So the less format you have to convert, the better are your chance to get something representative of your original CAD at the end. So in this case, I will just take parasolid file. So I don't know if you noticed, but it was something like 100 megabytes. So it's not a dummy model. It's a beautiful baby, I would say, but we can master it here with a simulation tool. So in this case, you have many approaches that you can use. You can go, as I said, really focusing on the precision and very detailed geometry. You can also use a simplified way. So in this case, this is the gearbox that we are talking about. So here we have the housing. We have the internal fluid vein, so standing for the air inside the system. We have all the gears and the bearing stuff. Actually, I could remove it because here we will focus on the e-motor, but that would be no fun. So I will just let it. Okay. Talking about the electric motor, here regarding the cooling system, so we have the plate containing the water jacket. So in this case, we wanted to check between two different designs for the cooling system. Here we have a first one with a U shape. And then we also want to compare it with more annular shape of the cooling system. So we just remove one of them. Okay. So now we are looking for this cooling system. And regarding the e-motor itself, so if we look at the stator itself and the coils, as you can see here, for the coils, once again, that's up to you. You can deal with the detailed geometry of the coils, depending on what you really want to achieve at the end of your simulation. But you can also work with an equivalent volume, depending on where is your more important level of interest. So in this case, I will just focus on the simpler one. And then we'll have a look on the moving area, I would say the rotor itself. So the rotor, it's quite simple because we'll have the rotor itself with the magnets. That's all. So we have the geometry here. And I don't really care if it's perfectly in contact, if we have intersection and small gap, as you may have noticed. For example, here we have the gap between the rotor and the stator. Then we will just specify to the software that we are interested in using voxel fitting measure. Then we will specify the materials for the different parts. So here we have a table including all the parts of my system. So here we'll pick all of them and we'll apply relevant datasheet. Here's a fluid vein inside the gearbox. It will be made of fluid. In this case, it's air. Regarding the fluid water jacket, it's fluid again, but this time it will be more liquid. So we can consider water, but we can also, for example, consider water glycol mixture. If you don't have the corresponding datasheet that you're interested in, of course, you can also create your own one and fulfill your library along your different projects. So here, as I said, a mixture of between water and glycol. Here, okay. Then for the housing and the plate surrounding the water jacket cooling circuit, here, we'll consider it as aluminum. Okay. All the gear, bears, and so on, including the stator and the rotor, we'll consider it as solid, but this time we'll take something like stainless steel. Okay. The coils, for sure, it will be considered as copper. And for the magnets, we'll just consider it as iron. That's it for the materials. Now we will create regions. So what is a region? A region is one or a group of surface that we want to clearly identify. It can be for multiple purposes. It can be, for example, to apply boundary condition. So in this case, we have the cooling circuit. Maybe we just want to identify the inlet. The same for the outlet. It can be also in a meshing perspective, because you remember, if you want, for example, to get a mesh that will keep and preserve the gap between the rotor and the stator, maybe it will be interesting to identify this area. So in this case, I will just remove the stator and just say, okay, the coil as well. We just say, okay, this area, I want to consider it because I will need to refine the mesh here. Okay, and the last reason for which we could have created a region is for post-processing purpose. For example, if you want to get, I don't know, maybe the average temperature, the heat flux passing through a specific surface, you can also create a region in that perspective. That was for surface region, but we can also create volumetric region, because here you can see that all the parts are detailed in the CAD assembly. But for example, if we want to consider all the heat loss that JMAG have been able to calculate previously, maybe it would be interesting to create a group with all the parts that will dissipate some heat losses. So in this case, I will just create a group here, Emacs solids. That's it. Now we can set up the simulation itself. So here we have a condition wizard that will help us to put the main outlines of the simulation and really to set up the simulation itself. So don't worry, I won't explain each of these panels. I will just remain focused on the main ones. The first one, analysis type, this is where you can add or remove physics to be taken or not into your simulation. So here we'll deal with the flow, we'll deal with the heat exchange as well. For all of this, you can also access to very advanced features and possibilities here regarding the solver. For example, you can deal with the way the turbulence will be modelized or not, at least it will be solved. You can deal with the turbulence model. You can deal if you are dealing with a coupled solver, uncoupled solver. So don't worry if what I'm talking to you doesn't ring any bell. Don't worry, because you don't need to be a PhD expert to be able to run the software. Of course, if you are, you will be delighted to get access to all of these options. But we are also here to advise you and support you on the daily purpose so that you get autonomous on your own applications. So that's for the physics that we can consider. Of course, you can also add more physics like moving elements, free surface, cavitation, and so on, but that's not the subject of today. In the basic settings, you can choose here if you are dealing with a steady state simulation or transient simulation. Here we'll just remove on the steady one. Now let's jump on the boundary condition. For the flow boundary condition, that's where it was important to give understandable name here for the regions. What about the inlet? What do I know about the inlet? Do I know a level of pressure, maybe a level of flow rate? So here, maybe I want to specify that I have 2 liters per minute passing through my cooling circuit. Regarding the temperature, maybe I know that I have something like 60 degrees at my disposal, okay? On the outlet, maybe I can just give a reference pressure, and that's it. So that's for the flow boundary condition. Now let's talk about the wall boundary condition. Here for the wall boundary condition, you could, for example, consider that some parts are in motion, even if we are dealing with a steady calculation. In this case, you remember that we remain with a steady calculation. But for example, if we have kept here the small air gap between the rotor and the stator, maybe it would be interesting to specify that the outer surface of the rotor, it's not static. Actually, it's rotating. And for that, you could specify a velocity here for the rotation. You can specify as well the axis for the rotation, but it will automatically suggest you something based on the CAD itself. Okay, so you could put it as it. So that's for the wall boundary condition. Now let's talk about thermal boundary condition, because you remember here, if we are not really interested to keep the air gap modelized with cells and so on, maybe we can just modelize it. So we could say in the same perspective here, the outer rotor surface, I want to add an extra thermal resistance between the rotor and the stator, so that I don't need to mesh quite finely here to catch the small air gap, but I just want to modelize it. I'm just looking maybe to compare 2 configurations to get the answer, who is the best. Maybe I don't need to go that deep into precision. So that's how I can set up here the different thermal boundary. Now let's talk about the source condition. So Didier did a great work on JMAG to get the heat losses inside the system. So here we could say, okay, on the rotor, I know that I will have to dissipate this amount of heat. But since Didier did a great work here, we'll just defer to that, and we'll say, okay, this Emacs solids, you remember, so I just group all the solids of my e-motor here. I will just say, okay, this volume, I will add some heat source to them, based on the JMAG calculation. But here I won't specify the amount of it. I will just say I will map this information from an external file. So in this case, I will just say, okay, this file, you can find it here in the same folder. So I don't remember the name Didier gave to this file, but anyway, that's a file from Didier, and I can specify, in this case, it's an Actran input format. And that's it for the setup. Regarding the solver itself, of course, you can also have access to everything that will be done by the solver. It's not a black box here. You have access to everything that can be made. But the good point is that in 95% of the case, I would say you don't have to go that deep. And that's all for the setup itself. So now let's talk about the mesh. You remember the voxel fitting mesh? The great singularity here is that you will ask for a level of detail that you want to be kept or not. So in this case, we do it in two steps. The first one, we specify the local mesh density that we want at the end. It also stands for the level of detail that we want to be kept after the meshing process. So here I could ask, for example, for 5 millimeters elements everywhere. I will just create this octree. So here it's just a matter of seconds, and you will get a kind of preview of the mesh that will be created based on these values. So here, I will get quite soon my octree distribution. I have also, by the way, an estimation of the number of elements in my mesh. So here, this is a preview of the mesh that we'll get based on these parameters. So here, if I look around the gap, for example, okay. So the gap is here, and you can clearly see that here it's way too coarse to hope to catch this small gap between the parts. So here, if I want to keep it after the mesh, I need to refine the octree. If I want just to clean this gap, that's what maybe we need to refine a little bit, but that's the way we should do. But if we want to keep this gap, maybe we'll have to specify that in addition to this 5 millimeter cell requirement, we'll also ask for something finer here around the rotor. So maybe we just ask for something like 1 millimeter around this surface. Maybe for this, in the same perspective around the cooling circuit, because it's smaller in terms of size, maybe we can also ask for something finer. Okay. Then I recreate the octree, and the point here is to get this information in few seconds. There is no point to wait 5 or 10 minutes that the meshing process could last to, at the end, notice that, oh, no, it was not fine enough. So I need to delete my mesh and then recreate it. That's the point here, to save time. So here, as you can notice, we have something finer in the cooling circuit. But what about the gap between the rotor and the stator? Now you can see that I have something finer. Now I can expect to keep this gap. Maybe a little push would be required, but you get the drift here. We get something finer, so we can expect to keep the gap between these two parts. I will just jump back here to my presentation because there is no point in just showing you how the meshing process will occur. Here is just, I wanted to show you a typical mesh that we can get from voxel fitting. So in this case, you can see that here for the coil, I started with the detailed geometry. So we are also able to handle this kind of level of complexity. It just depends on the level of detail that you ask in the octree process. So here, once again, we have polyhedral mesh, so it can look like hexa mesh, but it's more polyhedral because it will fit the geometry, the original geometry, depending once again on what you have asked. In this case, you can see that we have preserved here the gap between rotor and stator, and we get here the cooling circuit mesh with the prism layer that you can expect from a CFD perspective. And of course, you have full access here to the number of prisms that you can insert. So at the end of the day, you get your beautiful result. So in this case, on this model, we get the pressure loss inside the cooling circuit that can help you to notice if it's realistic or not. Do you have at your disposal this pressure loss in your cooling circuit? Regarding the temperature of the fluid, can you expect something quite uniform in terms of thermal distribution? In this case, we have something like 30-degree difference in the cooling circuit itself, so it's difficult to hope something better in terms of temperature distribution within the solid parts. So that's for one configuration. But as I said, the point of the simulation is to compare different configurations. So here you can see that we can get the same results with a different CAD geometry. So in this case, it's just really easy to clone, I would say, our setup and just to replace what has changed. So in this case, the cooling circuit. And then basically you just have to rerun the mesh, rerun the calculation, and you get this same post-treatment level. So you know there is a joke in the CFD world saying that CFD stands for color for directors. But at this point, this is nothing more than that. But actually, no, you have the pressure loss, but you have only beautiful pictures at this point. So it's quite difficult for you to take a decision. What is the best one in your case? That's why we can go beyond this just simple colorful pictures and so on. Actually, that's still good for directors because they can feed the website of your company, for example. But in your case, you are more interested about getting values, getting some real figures so that you can rely on to take your decision. So here, in parallel with these 3D results, we also get analytical results, with figures quantifying what's going on inside the system. And you can also, for example, get some pie charts to know where the heat comes from and where it goes. If you are looking, for example, for the e-motor, you can see where the heat will go. Here, maybe 90% will go to the plate of the water jacket. This was the point. So, okay, it's working as it should. But out of this, you can get here real figures about the average temperature of the e-motor. So you can see that in this case, okay, this one is lower by more than 10 degrees compared to the U-shaped cooling circuit. But is it realistic? Because on the other hand, we get also the pressure loss consumed by this design. If the temperature is lower, but if it's too high in terms of pressure loss, it's not realistic. But at the end of the day, you will have to take your decision based on these figures. And that's a good point because you still have something to do. But as I said, we want you to focus on what really matters. Where is your value? Taking decision. I'm sure your value is not in CAD cleaning and getting a mesh out of this process of setting up the simulation. Your value is here to analyze results and take decision. In this example, I just show you two different cooling jacket design, but we can also, of course, expand a little bit. In this case, in this other example, we just took the setup, including the JMAG result out of JMAG, like Didier did previously. We just give it as input to our setup. We run the calculation. We get, of course, beautiful colors and so on. We get also analytical results from which we are able to take decision. So in this case, it was the housing. Of course, it will affect the classification of the e-motor, but once again, that's your role here. And then you are able to compare the two designs to see, are you going in the right direction? So my final slide here, if you need to take if you need to remind some key points about what you have seen here, the CFD will allow you to explore different cooling configuration, because here in this case, it was water glycol mixture running into a cooling circuit. You can, in the same perspective, compare the same design, but this time with oil running through the cooling circuit. You can also explore, for example, the air cooling. So with CFD, you can explore all these possibilities. We can also choose the level of detail that we want to place ourselves. If you are quite in a hurry in terms of result and decision, maybe you can just modelize the air gap. And as we have seen, it doesn't take you too much time to clean the CAD geometry and so on. It's just a matter of what you input in terms of simulation. So you can consider or not this air gap, but it will work the same for all the different aspects of this kind of problematics. We can consider and take the benefit of what we did on JMAG previously, because here in this case, we just map what we get in terms of heat losses due to electromagnetic forces. But we could also consider getting other heat source out of JMAG perspective. For example, with Romax software that Sami will tell you more in few seconds. We could also expect, for example, to take into account heat source in the bearing systems. And as a final bullet point here, just consider that you can consider the thermal effect inside the system itself. And that's all for me. So I will leave it to Sami now.
Thank you very much, Maxime. So I should be able to share my screen.
Yeah, now you should be able.
Perfect, thank you. I will share my presentation first. Do you see it?
We can see it.
Sorry, it's not in the right display mode. Sorry. Yeah, should be better. Okay, so I will say a few words about Romax software suite. So we have different products that I will share with you. I will say also a few words about Romax Spectrum, the tools that I will use for this demonstration. And we will jump into the live demonstration. Okay, and then Romain from FFT will say a few words about Romax acoustic export for Actran. So what we could do next within Actran when it is about acoustic analysis. So a quick reminder about Romax software. So basically speaking, Romax portfolio consists in 6 different products. So the first one is Romax Concept, which is for early stage driveline design. So really simple to use in order to explore in a matter of seconds and minutes different kind of transmission layout from NVH, from efficiency and from durability point of view. We have Romax Enduro as well for structural and durability analysis on any kind of gearboxes. So we can run component ratings, gears, shafts, and bearings, taking into account of the full flexibility of the full system, including bearings and casings. Romax Energy for accurate predictions of component losses, lubrication design considerations, drive cycle analysis according to the WLTP, for example. Romax Pin for advanced bearing simulations, mainly for bearing specialists. So it is widely used in bearings industry, in bearings manufacturer. And the other 2 different products that we do have is Romax Evolve, which is a specialized tool for electromechanical analysis of e-machines only. Within Evolve, you will be able to run durability analysis on shafts, on bearings, using standard. You will also be able to get power losses of e-machine bearings. And of course, you will be able to run the NVH analysis, such as with Spectrum. Okay. Spectrum, it is the focus software that I will describe during the demonstration. Just a few words about Romax Spectrum. So usually you can hear NVH all the time. NVH stands for noise, vibrations, and harshness. And only Romax Spectrum can address the 3 letters of this NVH word. Okay, within Spectrum, you will be able to run vibration analysis in frequency domain, okay, without the need to embed other, to link with other softwares. You will be able to run acoustic simulations. We have embedded a small part of Actran for acoustic simulations. And for psychoacoustic simulation for sound quality assessment, we can link Romax with other tools. Okay, so some features highlights. So within Spectrum, you will be able to model from scratch any kind of drivetrains, any kind of gearboxes, including gears, shafts, bearings, and of course, e-motors in this case. You will be able to predict excitations coming from gears, so you can run gears contact analysis within Spectrum, and in order to get the transmission error, which is an excitation which can produce some vibrations and some noises. You can also include e-machine excitations. So in this case, we will interface with tools like JMAG, for instance. Then you will perform your vibration analysis in frequency domain. So you will get the harmonic response at any point of your systems. And the last but not the least, you will be able to run also acoustic simulation within Romax without the need to link with other tools. And we used to say that it is a from gear to ear tool, and there is no need to interface with other tools when it is about NVH analysis. Okay, so let's move on the demonstration. So we've seen the electromechanical part from JMAG, from Didier, and we've seen also the CFD calculations using Cradle just right before this demonstration, and I will stay focused on this NVH analysis, okay, for mainly structure-borne and airborne noise issues. If we break down this process, we can look at, first of all, the electromechanical system. So in this model, we can include all the components, which is basically bearings, shafts, and gears, flexibility of casings, and of course, we will include the e-machine stator. So I will demonstrate you how to include the e-machine into Romax, linked with the existing gearbox model. And then we will import e-machine excitations coming from JMAG. Okay? We have a seamless interface with JMAG, allowing us to import the e-machine excitations in a matter of seconds. I will not cover this part during the demonstration, but what we can do also is to calculate gears excitations and also adding other kind of excitations into the Romax model. So from this static analysis, we will get the system deflections, of course, but more importantly, we will get the component and system stiffnesses. Okay. And then we are ready to move in the NVH world to make the dynamic analysis. So first of all, we will set up the dynamic condensation for all finite element components. Okay, we have a finite element solver embedded into Romax, so we can solve it into Romax, and we will perform the dynamic analysis in frequency domain. Okay, and the outcome will be obviously to have structure-borne parameters and metrics such as harmonic response, ODS, bearing dynamics, dynamic TE, MSV, etc. And we will look at also the acoustic, the airborne noise issues such as sound power and sound pressure. Okay, let's jump into my Romax models. I will share. Sharing, I will share again. You should be able to see Romax. So yeah, first step will be to add the e-machine geometry inside Romax. So as you can see, we have the gears, which and the bearings. Of course, we can model the macro and micro geometry of gears. We can simulate also bearings nonlinearity stiffnesses. Okay, we can pick some bearings into a specific catalog. We have more than 60,000 bearings embedded into Romax. But my main duty here will be to add the electric machine. Okay, so I can go into modeling, powertrain, electric machine, and I will create from scratch. Okay, so I can update all main parameters, number of slots, board diameters. All these parameters can come from JMAG, of course. Okay. I will then connect the virtual component. For the time being, it is just a virtual component to my existing input shaft. Just putting my connections. So I can add a connection between the rotor and the input shaft, as you can see here. So this rotor is, as I said, sorry, this one is a virtual component. Okay, so in this virtual component, we can define properly the mass, the inertia, and the width, of course, which will be used for accurately predict the dynamic behavior. Okay. However, if you have further information regarding the rotor, it is my case. I got some rotor definition from JMAG, so I can interface with JMAG by using CAD Fusion. So I will just import the right rotor geometry, okay, using the CAD interface. So I will just look at the CAD that I got from JMAG. Just remove the machine, the gearbox, and I can see the windings, the stator, and of course the rotor. So I will just pick the rotor, and I will just include it into my Romax model. So as you can see, Romax will mesh it. Okay, I can mesh it very quickly. without the need to go into another software. Okay, I will click OK. So it will set up the position automatically. I will just do it by another way. And make proper connection between the input shaft and the rotor shaft. And I will make another connection between the rotor, the virtual component, and the rotor shaft. Okay, my next step will be to add a stator to my model. So, for example, my stator can be modeled as conceptual stator. So we will use Romax to simulate the stator geometry. We can also implement more complex stator shape by using the same interface as I've shown you by just importing from the CAD. Okay, your stator geometry into Romax, meshing it to Romax. Okay, so in this case, you will be able to simulate. So you will be able to simulate the orthotropic material that you can get on a specific stator geometry. Okay, in my case, I will just add a stator, a conceptual stator. This conceptual stator will be meshed into Romax and it will be connected to the inner diameter of your housing. So I will just select my housing. Okay, and I will have to update few parameters for my concept stator. So outer diameter of my concept stator, inner diameter should be okay. Length will be 170. So again, all these parameters are coming from JMAG. And select my material. And then Romax will connect this stator to my Romax model. Basically speaking, it will connect the stator to the housing. So as you can see, it has been meshed. And we can now see in 3D. So we just show the stator. You can see that we have added the stator geometry as well. As you can see. So we have now the rotor model into Romax with its own mass and inertia, and we have also a connected stator where we will apply the excitation coming from JMAG software. So it will be the next steps. Okay. So basically speaking, I will select my load case. So my load case is my static load case. So in this case, I have 30 Newton meters, 12,000 RPM, and I will import excitation from a third-party software. So in this case, I will import directly from JMAG my excitation. So just going to my JMAG excitations, I will get what I got from JMAG, which means for different operating point conditions. Okay, I will get some forces, radial forces, tangential forces, actual forces, possible, and of course torque ripple. So what I can do, I can just also calculate harmonics, and I will choose how much harmonic I want to extract from this preprocessor, and this harmonics will be used during the vibration analysis. So I will select just 5, and we can look at the harmonics which will be exported into my Romax model for vibration analysis. We can also have a look on the two signal animations. Basically speaking, we have the original signal, which is a time domain signal, and we will make a kind of breakdown into harmonics. And because we are making our simulation in frequency domain, we have to use harmonics into our Romax model. Okay. We can look also to the torque ripple, tangential forces, or radial forces. I will just click on accept. Okay. And that's it. So next step will be to make the dynamic, static, and dynamic condensation of all my finite element components. Okay. So in this case, I have my gearbox housing as a finite element component. I have my rotor and a gear blank, a specific gear blank, which is in FE. So in order to extract the static behavior and the dynamic behavior, which means system mode shapes and all natural frequencies, I need to run what we call a condensation. Okay, and you can do it within Romax as well. So in this case, just going to analysis, dynamic analysis, simulation options, and you can recover the parameters for these specific dynamic condensations. You just have to select the range of frequencies, okay, from 0 to 10,000 Hertz. Okay, and of course, if you want to display or not the 3D mode shapes. Okay, so by doing that, Romax will condense for all finite element components for a specific range of frequencies in order to get the natural frequencies of my system. Okay, so this part can be done internally at Romax. Okay, we have a specific solver, FE solver can be used. Or if you have a specific solver, we can also export the calculation sheet from Romax into your own finite element solver. Okay, so it is possible to export some calculation sheet from Romax, and you can use your own finite element solver. So we can export in a DAT file, so an Actran file, or other files, allowing you to do such external condensation. I will just jump into my other model, which is the same, but with my finite element model already condensed. Just find my Romax model. Find my. I will share everything, by the way. So you should be able to see my my model. So everything has been condensed. So all my finite element has been condensed, as you can see, until a specific range of frequencies. So I'm ready to start the simulations using the JMAG excitation. So I will just select my load case, and I will go into analysis, dynamic analysis, and vibration analysis. So it is a live demo. So all the calculations are made in live. So it is the real-time calculation. So for the purpose of the demonstration, I will show you some specific results that we can get from Romax, from the Romax Spectrum analysis software, especially for illustrate the effect of the electric machine excitations that we can recover here. So the first results we can look at is the mean square velocity of the housing surface to each of the excitations considered here. So which means torque ripple, radial force shapes, and unbalanced loads. Okay, so I will go into the mean square velocity. So mean square velocity provides a very good measure for radiated noise, and we can use it for optimizing the housing. Okay, so I will just select some excitation. So the unbalanced load, mean square velocity, look at in frequency domain, in frequency range, and update. So as I said, the mean square velocity is related to the potential acoustic radiated noise, which can be used to qualitatively benchmark different solutions. Look at the speed range. So normally we should see the amplitude increasing as the shaft speed increase. Okay, this is due to the fact that the unbalanced load is linked to the centrifugal effect, which is linked to the rotor speed. Okay, we can see the amplitude. I will add another tab. We select the torque ripples, okay, which we've seen before in the preprocessor that the 48 torque ripple harmonics was the most dominant one. So I will expect to have some peak at this specific harmonics. And I will display again the mean square velocity according to these two different harmonics. So right after the mean square velocity, we can look at the acceleration response at the housing mounts. Okay, for structure-borne assessment. We can also look at the harmonic response at some accelerometers. Yeah, we can see a peak close to 7,400 Hertz, and some peaks at very low frequency range. Okay, and we can see that the peak is slightly above what we get from the unbalanced load. Okay, so we will look at some accelerometers results as well. So we can go into 2D. I will keep these harmonics because we've seen that these 48 harmonics are the most dominant one compared to the unbalanced load. Of course, if you want, we can also include TE excitations as well. Let's stay focused on the image forces. So we have different response nodes here. These response nodes are basically virtual accelerometers, okay, across the full system. So these response nodes are positioned around the gearbox housing. You can have a quick look. Normally, you should be able to see red points. So we have different response nodes. So one on the inverter, one close to the motor, e-motor flange, and other close to the mounts, they close to the input shafts and close to other bearings. So for correction purposes, but also for optimization purposes, we can look at these specific response nodes. So I will look at this response node for the same harmonics as before. And I will click on Emulate. So normally, what you can do is to look at the normal to surface vector instead of vector magnitude, or instead of tangent to surface. It will also provide some good measurements of the potential radiated noise from the housing around these specific nodes. Okay, and therefore provide some insight to improve the housing design. Okay, and of course improving the NVH performance. So yeah, it's take a bit of time because I'm just plotting two excitations at the same time on 1, 2, 3, 4, 5, 6, 7, 9 or 10 different points. Yeah, this is it. We can see a peak on a specific node, which is this node 28763. This node is located very close to the motor flange, e-motor flange, which means here, really at the center of this motor flange. And because these node locations has a large, fairly flat surface, it will likely to generate significant radiated noise. So it is something we can have a look later on during the acoustic simulations or the ODS calculations as well. What we can do also is to plot some results on the mounting support. So we have 3 different mounting supports, as you can see here. We have one close to the input shaft, one close to the e-motor, another one close to the differential case. So if you are expecting to have some structural borne issues, we can have a look on this specific mounting support as well. So I will just click, select these 3 different boundary conditions for the same harmonics, and we click on update. And we should be able to see the amplitude on these 3 different mounting supports. Should be done. So of course, the calculation times is really dependent of how much harmonics you are selecting, how much points you are plotting, and of course how much elements you have into your Romax model. Quite quick. So we can see that we have some peaks still around the same range of frequencies, so between 7,000 and 10,000 Hertz. We have large peak on the the blue curve and the green curve, which are close to the e-motor component and close to the diff mount. So it is something that we can have a deep look in the next tab. So what I can plot as well is the ODS, so the operating deflection shape will show us the vibration response of the whole system at a specific frequency, at a single frequencies, basically speaking. So we've seen that we got a large peak at 7,400 Hertz. So we are expecting to get some radiated noise issues at this specific frequency range. So I can look at this specific frequency range. So I will just select the right frequency. And we can have a look for the same harmonics. So, and we can make some animations, and we can clearly see that at this specific frequency, we have some vibrations of the outer ribs of the electric motor housing. Okay, so it can generate some noises as well. So next is to look at the ODS at these specific frequencies, where we are seeing a peak close to the e-motor flange. Okay, at 8,900 Hertz. And at this frequency, we are seeing also a significant vibration from this flat surface. So again, we are expecting also to get some issues, some noises issues coming from this flange of the motor. So next step will be to make some optimization, so we can change the ribs around the housing. We can import again the housing, making again the simulations, and looking at the same metrics that I've shown you before to improve the vibration and potential noise issues. Next step is to run the acoustic simulation. So I will be a bit fast. So I've shown you the vibration analysis. We can look at the acoustic analysis. Okay. So using the Actran solver, so we have embedded a small part of the Actran solver. We can select the gearbox housing because we want to display the radiated noise coming from the gearbox housing, and we can select different excitations. Okay, you can select the minimum and maximum frequency range of interest, and you can run the simulations. So the first step will be to generate the shrink wrap mesh. Okay, and Romax will be able to show you the shrink wrap mesh, and if it is enough in terms of accuracy, you can just leave it like that and running the acoustic simulations. So the acoustic simulations can take a bit of time. So again, it is dependent of the number of elements in your housing. And in your finite element components, it will be dependent also of how much connection you have between your finite element and your Romax model. What kind of elements, what kind of connections, RBE2, RBE3 connections. So normally you should jump into, sorry, I will share again. You should be able to see again my screen. So normally you should be able to check the shrink wrap mesh, as you can see here. Okay, if you are satisfied with this kind of meshes, you can just use it. We can look at the structure meshes. Okay, and then in terms of post-processing, you will have the 2D plots. Okay, so it will display for each microphones the pressure for any microphones. Okay, so we can select excitations. You can play with the excitations. Okay, we can look at the sound power level as well. Okay, and in this 3D waterfall plot, you will see the entire speed frequency plane with all excitation orders. So it's like a Campbell diagram. So let's just changing a bit. So we can look at for each harmonics the sound pressure, the sound power level. Okay, and below in this 3D microphone plot, we can look at for each the directivity of the sound. So for each arrow, you will have microphones. Okay, and we can look at how much amplitude will be for each microphone as well. And interpolate with a sphere. And look at for each excitation order. The directivity and the variations of these sound directions. I think I reached my time. So let me share again my presentations. Just to sum up a bit. Sorry, yeah. So we've seen how to include an electric machine into Romax, into an existing Romax model, which include bearings, shafts, gears, and casings, and all other components. We've seen also how to implement e-machine excitation coming from JMAG, and how to perform in frequency domain, vibration analysis, and acoustic analysis very quickly. So to sum up a bit, so Romax Spectrum is a very fast model, fast solver, very quick to build, as you've seen, very quick to import other inputs from third-party softwares, and quick to run. Okay. More importantly, we will consider the full system and the whole powertrain during this simulation. It will give you some answers in order to identify problems and help you to resolve issues. In terms of trust, of course, we have made some good correlations between Romax Spectrum and other test data and correlation data. And by the fact that we can include in a seamless way excitation coming from JMAG, it will also reduce errors when importing in-machine excitations. And in terms of process, we can link Romax with other tools, as I said, with Actran and with JMAG, which allow us to be very powerful when it is about full system analysis in PH purposes. Okay, so next slide is about how we can do further in terms of analysis when it is about linking Romax with Actran, the full software suite. So I will let the floor to Romain.
Hello, Sami. Thanks a lot. Can you hear me?
Yeah, very well.
Okay, super. Thanks for your introduction on Romax Spectrum and actually your detailed analysis on the components. But now I will quickly talk about why it's also interesting to move forward in your acoustic analysis. And the main reason for that is that actually our powertrain is not an isolated component. So if we look at the total noise that we have within a vehicle, well, obviously the powertrain will contribute to that, and we'll have two main contribution paths to the interior noise level. One of them is what we call the airborne path. So it will be the sound that is radiated by the powertrain that we can analyze within Romax Spectrum, but without considering the complex environment where the powertrain is actually installed. And this is why it's interesting to move forward in acoustic analysis to basically consider potentially acoustic treatment that are around this powertrain, consider the vehicle geometry, including also the road it is driving on. And obviously combining these acoustic sources with other ones if we want, such as tire noise or other equipment of the vehicle. This is what we can do in Actran, and we'll see that later on. Additionally, there is another path that will generate noise inside the vehicle, and this is what we call the structure-bound path. So it's really vibration that are transmitted through the chassis of the vehicle that will be impacted by acoustic treatment as well, present in the vehicle. And therefore, when we study this type of contribution, we are keen to understand trim body responses, better identify the transfer path analysis, and because we deal with also more and more electric powertrain, reach mid and high frequencies. So this is what we can do actually thanks to the complete Hexagon CAE portfolio solution. And if we move to the next slide, we will see that actually it's super easy thanks to the connection of the different solutions we have to increase the collaboration in between the powertrain department and another NVH department. So indeed, Romax Spectrum can easily output dynamic mounting forces that can be used for structure-bound path, typically done within MSc Actran, that can be coupled with Actran for advanced interior acoustic analysis, considering all acoustic treatment that we might have. And Romax Spectrum also can output an Actran file that is ready to be used within Actran for more complex exterior noise analysis. And the last point, so the exterior noise analysis within Actran is the one I would like to a little bit highlight within the following slide. So if we move to the next slide, well, we will understand how we can easily set up an exterior noise analysis starting from Romax Spectrum analysis. So in Romax Spectrum, we are within what we call a free field radiation scenario. But what the user can do is actually export a file that can be used in Actran to perform what we would call an in situ radiation scenario. So Romax Spectrum will output several files. As I said, a needed file, which is an Actran input file, together with the deflection shape, so information about the vibration of the structure. This information can be used within Actran, and we can add around our powertrain, for instance, the vehicle that we want to analyze for our analysis. So those two meshes will be combined. And if we click just once more, please, Sami, then we will create, and again, a more complex model where we would have our powertrain that is installed within our vehicle. And therefore, we can add more, let's say, complexity or different effects we would like to study, such as the road effect, any acoustic treatment effect that we might have in the engine bay, other noise sources, as I said earlier, such as tire noise sources that we could study at the same time as the powertrain radiation, and obviously considering the vehicle, the geometry effect. So how the vehicle geometry and design will impact the external noise propagation. So thanks to that, well, we can look at different indicators within Actran. So obviously we can look at how the sound is propagating through maps and directivity maps. We also have included dedicated automotive indicators such as pass-by noise responses, where automatically the user can have access to the pass-by noise performances of the vehicle. If we deal with acoustic treatments, well, we can assess the performances of each of them and rank their efficiency as function of the frequency to really understand which one is contributing the most as function of the frequency, and therefore which one we should pay attention on in order to potentially optimize it based on the frequency and the goal we want to reach. And yeah, and finally, we can also look at more advanced part contribution of our system to really assess which part of, for instance, our powertrain is radiating, again, as function of the frequency, to ease the optimization process. So that's a quick overview of everything you can do with Actran. Really here, what we need to remember is the easy coupling we have in between our components design tool that is Romax Spectrum, and how to link it to a more advanced acoustic tool to perform global system analysis. So that's all I wanted to give you as an insight today. And of course, if you have any question, please feel free to reach.
Thank you very much, Romain. So I think we covered all about Romax Spectrum and the link within Romax Acoustic, which is a part of Actran, and also the link with the full Actran software suite. Thank you very much, Romain. I think it's time for Q&A. Didier, do you want to take the end?
Okay, so thank you for this good presentation. I think we have some, now we can switch to the question and answer. So I have some question about noise design. The question is, can you also hear it, especially for noise design?
Didier, is it a question in the
Yes.
chat?
Yes, from the chat.
Okay, let me just have a look.
If you open the you have the QA box, question and answer box, you will see.
Okay.
On the open tab, you have. Can you also
Yeah,
hear
so
it?
the noise design. So yes, we can hear the noise. So it's not directly done within Romax. However, we can interface with other tools, as I said before. So in this case, we will interface with VI grade. So we can export the full system from Romax, and it will be linked to another tool. We can also export from Romax into Alter and VH Director. So in this case, we will be able to export the excitation data, but not only FE meshes and everything for psychoacoustic purposes. We have So it's basically some export options, direct interface, seamless interface with other tools for psychoacoustics. So yes, we can do it, but using other tools as well.
Worth to mention, Sami, to complement your answer, indeed we have, I mean, Hexagon has a strong partnership with HBK, so for VA Grid and the NVH simulator. In Actran as well, you can listen to the results, either for a component that is isolated and radiating in free field, or for a more complex system. You have integrated within Actran the ability to generate sound file to listen to the result of your design.
So just got another question. So is any validation of Romax Spectrum available to share? Yes, we do have further webinar on our romaxtechnology.com website. We have done, we got a very good testimonial coming from different companies. So GKN, but also Renault in France, Lucid in the US, and other big names are using our solutions today to predict vibrations and noises. And all these case studies are also available on the website, on the romaxtechnology.com website. Another one I got from...
Yeah, I see one that is related to structural noise and the kind of the frequency we are talking about when we talk about noise and structural noise. And the question is, what do you consider to be mid and high frequencies? That's actually a super good question, and actually it's not that easy to answer, and I'm sorry for that. But one way to distinguish what we call about low, mid, and high frequencies is to look at what we call the modal density. So how many modes do we have within those frequency range? Typically, low frequency would be a frequency range where we can easily distinguish the different modes that we have for the structure, while high frequencies will be a frequency range where we have such a dense modal density that it's super tricky to distinguish which mode is contributing to the noise, and therefore other type of analysis are required to better handle those behavior. And typically we talk about energetic analysis. So when we look at the noise within a vehicle, well, noise from every frequency is contributing to the total noise within the vehicle. Structure band path is one contributor, but now with the excitation from an electric motor that is at higher frequency, there is actually a contribution from the structure band path inside the vehicle at high frequencies. I know it's very high level answer, but if you want to know more about our solutions that we have within Hexagon to tackle with low, mid, and high frequencies noise, just feel free to reach, and then we can have a dedicated session on that.
Can see another question from Michael. Was the condensation step in Romax FEM modal analysis? Yes, it is, definitely speaking. So for all finite elements, we have to condense using a CMS method. So it's quite standard methodology to get all the system modes, shapes. So yes, we are using this methodology to get the modal analysis into Romax. However, as I said, if you prefer to use your own solver, we can interface with them. So it's not an issue to prepare the Romax model, which means to make the condensation nodes, master nodes, slave nodes, connections between Romax components, such as bearing outer raceways and your finite element model, which in this case is the housing, and export this calculation sheet into another solver. And then we can import back the stiffness matrix and the mass matrix from your third-party software into Romax for further analysis. So yes, it is a FEA modal analysis that we are performing within Romax. I think it's pretty much it.
Okay, thanks. I think if you move from the chat box, you'll also see some question, but I see that Sami already replied to some question. I think I have some question from the chat. Is any validation of Romax Spectrum? I think you already replied to that, right?
Yeah, I can share if you wish a further correlation we did. As I said, we have some case studies available online with different customers. So with Renault, with DKN, with Hyundai as well. So feel free to go on our Romax website to look at these case studies. If you want to know more, just feel free to send me a mail, and we can arrange a deep presentation of some correlation we did.
Okay, thanks. Any other question? No. No, so maybe we can close the webinar. So thank you for joining this webinar. So if you have any question, please you can also contact us by email if you want. So thank you for everyone.
Thank you, Didier.
Bye-bye.
Thank you all.
Thank you, everybody.
Thank you.